and Comonadic dependent type theory. And intuitively, what we're talking about here is, well, in the case of adjoint dependent type theory, instead of having a dependent type theory which is interpreted in one category, you have kind of two kinds of types, and they're interpreted in two different categories, and there are operators that allow you to pass from one category to the other that are adjoint. And then Comonadic dependent type theory is pretty much what it sounds like there. It's a dependent type theory where there's a comonadic operator. And just a quick note on terminology. So, I mean, one thing that I want to highlight that's in common with those two kinds of type theory is that you have these operators which you think of as functors. And so basically for any type theory where you have operators which are interpreted as functors, I'm going to refer to that as a modal type theory. Normally, people would think of a modal type theory as being a type theory where you have some endofunctor on the model, but I think there's no real reason to restrict to that level, and somehow talking about functors rather than endofunctors is a natural thing to do. So this work is pretty application driven, actually, so that's sort of why I was motivated to want to present here. I think there's actually a few different sorts of things you could maybe apply this to, but what really got me into it and what I wanted to highlight is the connection to natural language semantics. So intentional logic is a kind of a higher order modal logic, which has been used in natural language semantics, so to model natural language meaning. And in some prior work at CMU, we had sort of connected this to Comonadic type theory and developed a topos theoretic semantics. And so this work was based on a desire to extend that to dependent types and to use dependent types to model natural language meaning. Okay, so the mission here is to model these type theories and to develop a notion of model, which is some kind of a categorical something. And I think that the picture which emerges is basically in keeping with the notion that these modal operators are intuitively functors between categories of types. The notion of model should be that you basically have potentially well, in the case of a general modal logic, you have a bunch of different categories of types, and then you have that you can model dependent type theory in, and then you have morphisms of the models that go between them. And so the way that I want to make that precise is to work with natural models, which are just a categorical formulation of categories with families, which is one of the more popular ways of modeling dependent type theory. And in terms of the morphism, I'm going to work with weak morphisms, which are just a kind of notion of morphism for categories with families or natural models, which has been previously proposed. And so I'm going to focus on modeling adjoint type theory in this talk because the story is the cleanest. But I think that there's some greater generality that you can use this notion of weak morphism to model modal type theory with. So I've just been sort of gradually accumulating some examples. There's the adjoint type theory and the Comonadic type theory. There's also this work of Klooston et al. Where they model a kind of modal type theory of an endo-adjunction. And so I don't know exactly how far you can push this, but at least for these three cases it works. And then I'm going to stop saying weak. Okay, so that's the outline. So I'm going to talk about natural models, then the type theory, then the interpretation, and fortunately we already did the introduction. Okay, so as I said, a natural model is essentially a category with families. It's a categorical way of thinking about categories with families. So what it consists of is a category, which is kind of like the category of context. The objects are context, and it has a terminal object, which interprets the empty context, and then it has some presheaves of types and terms, or you think of the elements of those as types and terms, and then you have this natural transformation P from terms to types, so that kind of assigns each term to its type, and then that natural transformation has the property that is representable. More on that in a moment. That's really doing a lot of work there, but just wanted to introduce a little bit of vocabulary first. So an object of this category C in a natural model we can refer to as a context. Of course, we're working semantically, so it need not literally be a context, but yeah, just a way of talking about it. So if you have an element A in tie gamma, so an element of this presheaf of types, you call that a type. And in this case, it would be in context gamma. And then if you have an element of the presheaf of terms at gamma, such that this P natural transformation assigns this little a to big A, we'll say that, okay, well that's a term little a of type big A in context gamma. And so actually in this natural model perspective, we use the Untitled lemma a lot, and we view the elements of these presheaves as natural transformations from representables. So we're going to sort of freely conflate elements of the presheaf with natural transformations from representables. So for instance, like this big A, we'll think of as either an element in this tie or an element in tie gamma, or a natural transformation from Untitled gamma to tie. And so this equation here, when you translate into these terms, is saying that, well, little a followed by P is big A. Okay, and so this is what that representability condition means. It's a kind of a formalization, it captures the comprehension axiom of a category with families. So basically what it says is that if you have a type A in context gamma, then you can form this context extension, or this context extended by A, gamma dot A, and then that has a projection back down to gamma, and then you have also this V, which is basically you think of as kind of a variable introduction for a variable of type A, and if you think about what it is in this sort of UNATA perspective in the presheaves, then it's saying that when you form the pullback of P along A, then you actually obtain this this projection, and then the top part of the corner is the gamma dot A. And so all this data together constitutes the comprehension of the type A, and then this is the context extended, the extension of gamma by A, the context extension. Okay, and then we'll sort of need this notation later. So so again, this is what it looks like when you have a term little a of type big A, but you can go back and forth between elements of the presheaf of terms and sections of a comprehension. So yeah, so just as you can move from big A to its comprehension, you can move from little a to its sort of comprehension as a section. Okay, so morphisms of natural models. So these were studied by Newstead recently. And so first we're going to define a lax morphism, and then a weak or a morphism, I should say, will just be a lax morphism with a property. And so what is a lax morphism? So a lax morphism is a functor between the underlying categories and these natural transformations. So this shriek refers to the left con extension. So basically, when you have a functor between two categories, it induces a functor in the same direction on the presheaves. So you can think of that as sort of the extension of the functor to the presheaves. And so basically, remember, so tie here tie C. So this is like part of the natural model structure on C. So we want to have a way of turning types in C into types in D. And the way we do that is we transport tie C into the presheaves on D with this F shriek. And then there's this natural transformation, which you think of as taking those types in C to types in D. And similarly for terms. And then we require that this diagram commutes. Okay, and making a bit, or introducing some notation for what I was just saying, you can, so a lax morphism has an operation on types and terms. And so basically, if you have a type A, then you can hit it with this F shriek if you have this lax morphism F. So that takes it from the presheaves on C to the presheaves on D, and then you can post-compose with this phi, which comes from the lax morphism. And so this composite, I'll write like this, and we think of that as the result of applying the lax morphism F to the type A. And then you can do something similar for terms. And basically, these will be used for the interpretation of the formation and introduction rules for the modal operators that we'll look at.
Why do you write slash instead of okay?
Well, because so when I say implicated, I was trying to be vague, because that's not like literally how you interpret it. So we're going to define some further, simpler notation for the thing that you actually use to interpret. Okay, so we have lax morphisms, and now we want to define morphisms. And basically, the way that we do that is we know, well, okay, from the notion of lax morphism, there's sort of two ways that you can port types over and then realize as a context extension. So if you have right, so if you have a type A, you can form this F/A like we were just talking about, which is F, you think of as F applied to A, and then you realize it as a comprehension. Or you can first realize A as a comprehension and then apply F to it. So that's this. And so since this is a comprehension, it has this pullback property, and then it turns out that you can apply that and get this comparison map between those two ways of doing things. And then a morphism is just a lax morphism where all of these comparisons are isomorphisms, and it also preserves terminal objects. So that's what this is saying. Okay, so again, we're talking about an adjoint type theory. So we're going to have two kinds of types, which we think of as living in different categories. So we'll call those D types and C types. And then we're going to have not just D types and C types, we're going to have D contexts and C contexts, and D terms and C terms. Okay, so So for the D context, this is pretty much as you'd expect. So this is like we have a judgment for types that live in the category D, so to speak. And we have these special variables, which are like the variables for types in D. And then we have something similar for in C. But these C contexts are sort of wonky in the sense that they can also integrate D variables. So we have actually two kinds of variable judgments here. We have a variable judgment for the D variables and for the C variables. And I was very glad that we had this talk earlier about higher order modal logic, because they talked about rigid and flexible variables. And so this you can think of as a rigid variable, and this as a flexible variable. And so why is there this sort of asymmetry where for the C context, you can have this structure where you have, well, some C types which might depend on D types, but in the D context, you just have D types depending on D types. Well, so intuitively, I mean, it sort of makes sense to have something flexible depend on something rigid, but it doesn't really make sense to have something rigid depend on something flexible. And so if you think about how that's cashed out in the Kripke semantics, that sort of gives you an idea where to have variable types depending on constant types, that makes sense, but it doesn't really make sense to have constant types depending on variable types. Okay, so yeah, so we have these sort of more complex contexts in C, and so we're going to have types and terms which depend, which even though they're C types and terms, they're going to depend on D variables ultimately. Okay, and semantically, what do we think of a judgment like this, which depends on D variables and C variables? Well, okay, so actually what that context will be interpreted as is you have an interpretation of the D part of that context, and then you port it over into C with the left adjoint, and then you build the rest of the context on top of that. And the type theory sort of forces that interpretation in a way, because we have this special rule for, which is the elim rule for the type form L, which basically says if you have a term which is of type L of A, then you can substitute it for a D variable of type A. So we think of the A as already being transported into C by L. So even though this doesn't literally match, it sort of spiritually matches, and so that we can do some kind of a substitution. It's not a genuine substitution, but it's a kind of a type mismatch substitution. So these are the rules for L, and that's the sort of curveball there. Okay, and then the beta conversion for L says, okay, well, if I have a D variable and a D term, there are sort of two ways I can substitute. I could do a kind of a D substitution and then move into C, or I could first move the thing that I'm substituting into C, and then substitute the D term, which I also moved into C. And so this rule says that those two things are the same. So you can first do a substitution in D and then move into C, or you can first move everything into C and then do this special substitution. Okay, and these are the rules for R. I guess the only thing to note here is that, well, because the C contexts allow this sort of more complex form, but the D contexts don't, if you're moving something from a C context back into a D context, it had better not have stuff that came from C. So you can only form an R of B if it was in a context where everything came from D. Okay. I was also very glad that the term geometric morphism came up earlier. This is my notion of a model for this adjoint type theory. And basically, it's just that you have two natural models, E and F, and you have morphisms going back and forth, which are adjoint. And you could say, well, why don't I just call that an adjunction of natural models? And my justification for this terminology is that, well, in a geometric morphism, the left adjoint preserves limits. And here, the fact that the left adjoint is a morphism of natural models, that's a kind of a preservation condition. And so when you're using geometric morphisms to interpret modal logic, you actually use the fact that the left adjoint preserves finite limits to get the fact that it preserves monics. And so monics are sort of your dependent types one level down, if you will. And so here, the fact that the left adjoint is a morphism essentially means that it takes comprehensions to comprehensions, if you will. So that's sort of analogous to preserving monics. So that's where that terminology comes from. Yeah.
So I'm trying to think maybe models in topoi. Then usually the push forward will not be morphism models, right? We want to preserve some geometric theory. So what is this trying to? What is a natural example of this?
Well, I mean, if we're talking about models of modal logic, then actually any geometric morphism gives a model of S4 modal logic. The geometric so it gives a single model of modal logic, which is induced by the comonad. So you can think of the model as living in the domain of the geometric morphism. Yeah, so in some sense, the morphism terminology isn't great there because it's giving you a single model, not a morphism of models. But anyways, well, let me just finish up, and then we can do questions. Okay, so I promised we would clean up the notation a little bit. So the thing is, the R-type former it isn't actually interpreted as R applied to a type. It's actually interpreted as R applied to a type and then pulled back along the unit of the adjunction. So that's what that's saying. And then for the interpretation, so we had those simple D contexts. So there, the interpretation is sort of exactly as you'd expect, using the context extension operation from this F natural model. You have to do something a little bit more complex to deal with the complex structure of the C context. So I actually interpret the one of these more complex contexts as an arrow in E into the interpretation of the left-hand side of the context, but ported over into E. But of course, what we're given in the data is just this natural model over E. So if we're going to interpret the types, we need to take the domain of that arrow and then look at the types that are living over that. So this is some kind of complicated bureaucracy about that. And okay, and then the interpretation now is completely as suggested by the notation. It's just you interpret L in the syntax by L in the semantics and so forth. And I'm basically running short for time, yeah, okay, I should say something about this. So the formation and the introduction rule we get kind of straightforwardly from the structure of the morphism of natural models. To interpret the elimination rule, we have to actually do something more ad hoc. And then here, what this is we say, okay, well, if we're trying to interpret the elim rule for R, we apply L to the term, then we realize it as a section. Then we use the indexed co-unit induced by the adjunction, which lives in the slice over L interpretation of delta, and then we turn it back into a term that's what this, so we turn it into a section, then we do something to it, then we turn it back into a term. And then this is the definition of that index co-unit. And that interpretation is sound.
Are there any questions?
Yeah, so kind of same question. So what is a natural model or natural model in the formal sense of these morphisms of natural models? How do they differ?
Yeah, I mean, so basically, an example that you would want for this would be like cohesion in homotopy type theory. So if you had there you have a comonad, which is like the discrete comonad, and you can decompose it into the global sections and the delta, the constant functor, and so that should be an example of this.
But that's a morphism of natural model, or that is a natural model? Because the push forward.
Well, so I mean, here this notion of a model for like adjoint type theory, it involves morphisms of natural models going both directions, and so those delta and gamma that we were just talking about, those would be like the underlying functors of such morphisms.
Are there any other questions? Yep.
So I expect linear, nonlinear type theory is sort of one of the motivating examples here where you want quantum mechanics at least. Are there other? So is that actually a motivating example for you guys, and are there others?
Well, so I mean, basically the type theory that I was basing off of for this AdTT is this Krishnaswamy et al. Linear nonlinear type theory. I mean, it's a little bit different how I presented it there, but basically it's kind of based off of that. So so seemingly this would have applications to that, but I would definitely be interested to discuss it further.
Any other questions? Yes?
This work with recursion is also to consider an extension where you have some term-level recursion, for example.
You mean like inductive types, or?
No, recursive types.
Oh, okay.
I mean, there's like in linear, nonlinear models, for example, it's possible to extend them with recursion.
Yeah, so I mean, I tried to set this up in a way where it wouldn't break when you add type formers, other type formers, but I couldn't tell you exactly how far you can push that, so I haven't considered that in particular.
Okay, let's thank the speaker again.
On the Hopper-Beanies algebras, this is an algebraic structure where basically